All right, so in this video, we are going to be starting a new topic, polar coordinates. It's going to segue into polar equations, and that'll segue into complex numbers. So I'm really excited. I hope you are. In this specific video, we are going to look at the coordinate system that we already know, Cartesian, and how that compares to the polar coordinate system. We're going to describe points in space in a new way. After that, we're going to graph polar coordinates. We're going to get some practice with that. We'll look at some basic polar equations, nothing too complicated, lines and circles and stuff like that. We'll talk about why polar coordinates and polar equations are convenient. And we'll finish the video by looking at how to convert from what you already know, the Cartesian coordinate system, to the polar the polar coordinate system, and vice versa, polar back to Cartesian. So those are the topics that will be discussed in this video. This is lesson number 1 in my lesson sequence, if you're following along in the packet. And last but not least, if you are reviewing this information in the textbook as we go, 796 to page 803 is where you'll find the introduction to polar coordinates. Let's get started. So, quick review, we have been using the Cartesian coordinate system all year to describe the location of a point in space. So if I have a point over here, let's call it like A, we have described this location based on its distance from the y-axis and its distance from the x-axis. So the distance from the y-axis is what we call the x-coordinate. And the distance from the x-axis is what we call the y-coordinate. And we describe the point A using those two things. So how far right do we go and how far up do we go? But polar coordinates allow us to describe this point using two completely different numbers. So instead of a how far right do you go and how far up do you go, is there another way that we can describe this location? And I'm sure there's many, many ways, but the specific way I want to look at here is how far away from the origin am I? We're going to go ahead and call that, I don't know, r for radius. And what is my angle with the positive x-axis? If you give me these two numbers, which we usually write as r comma theta, you can describe this point right here. If you give me a length away from the origin and an angle, you can describe coordinates in space. This is an alternate way to describe points in space. Quick example, let me just knock an example out. I think it helps make this make more sense. If I give myself a coordinate like, let's say, 2, 4, we can describe this point saying 2, 4. That's the traditional way, Cartesian coordinates. A length away from the y-axis and a length away from the x-axis. But we can also describe this point as a distance from the pole, the distance from the origin. The name that we gave this is pole, and an angle from the positive x-axis. I'm going to go ahead and write those down. This is called the pole, and the positive x-axis we call the polar axis. But that angle, we can figure out what that is with a little bit of trigonometry. Okay, so 2, 4 is one way. But also we can use, well, what's this length? Pythagorean theorem, right? 2 squared plus 4 squared, all square rooted, which is going to be 4 plus 16 square root of 20. All right, so we can describe this point as the square root of 20, comma, well, what's this angle? Theta. Well, it is the tangent of 2 over 1, tangent of 2. So, sorry, not the tangent of 2, the arctangent of 2. So I'm going to go ahead and just write arctan of 2. Or if you want to make that that number there make a little bit more sense, I'm going to go ahead and break a calculator out. Arctan of 2 is 1.107. So at 1.107 radians. And we could move that into the forbidden DEGREES. But I'm going to stay away from that. Root 20, arctan 2. So we can describe points, long story short, using this new coordinate system. All right, so let's go ahead and graph some just to get used to this thing. So I've gone ahead and I've made a polar coordinate graph. You'll get used to these concentric circles. But let's go ahead and graph some points. So first point I want you guys to graph is 3, 2 pi over 3. So that says go 3 units out and have an angle with the x-axis, or what we call the polar axis, of 2 pi over 3. So 2 pi over 3 is going to be, that was 1 pi over 3. 2 pi over 3 is going to be somewhere around here. All right, 2 pi over 3. And 3 units out, the nice thing about the polar coordinate system is these concentric circles are all 1 unit apart. So 1, 2, 3. There's our coordinate right there. I'm going to go ahead and change the color. This is right here. Cool, let's do another one. Let's look at 2, negative pi over 12. So we'll do this one in, let's go blue, a light blue. All right, we're going to graph the point 2, negative pi over 12. So what does that mean? Still with the positive x-axis, the polar axis. So polar axis is right here. And we're going to go negative pi over 12, so in the opposite direction. So that's going to be roughly around here. And 2 out is going to be right here. Cool. So this is my point 2, negative pi over 12. So we're describing points in space using 2 numbers still, but those 2 numbers represent something else. They represent a distance from the pole and a angle with the polar axis. Okay. I'm going to do one more. The worksheet that goes along with this has 6 examples. Go ahead and do the other ones if you so choose. But I'm only going to do one more. Let's go ahead and do it in purple. Let's look at negative 4, pi over 6. All right, so this kind of hits on all the little nuances that I could throw at you. So now we have a negative radius. So what does that mean? That's going to mean instead of going in the direction of your terminal angle, we're going to go in the opposite direction. So pi over 6, it's about right there. But instead of going a 4 in the direction of this, we're going to go in the opposite direction. All right, so that's going to be 1, 2, 3. That's going to go right here. All right, so we can have negative numbers in this coordinate system. That's good because we want to be able to input negative things into polar functions later on. But we have negative angles, positive angles. We have positive radii, and we have radii that go in the opposite direction of our terminal ray. So plotting polar coordinates, not too bad. I do want you to notice one thing, though, and that is, and you may have already noticed this actually, but these coordinates are not uniquely described by a pair of a radii and angle. All right, there are actually other ways I can describe this point using a radii and an angle, especially since we have negative radii and negative angles. I can describe this point in actually an infinite amount of ways, and I ask you right now to try to think about another way to describe the point 3, 2 pi over 3 using a different set of coordinates. I'm going to go ahead and do that now. So I want to describe this point right here, this red point. So 2 pi over 3 is one way, but I could instead do negative 4 pi over 3. I often think about the angle before I think about the radius. But a negative 4 pi over 3 takes me to this ray again, and then I can go in that direction of that ray 3 units. So this is another way to describe that red point with a different set of coordinates. And I could keep doing this. I could use a negative radii length and instead use a positive angle. So I'm going to do one more. let's go ahead and choose yellow. All right, so instead of doing these two, I'm going to do negative pi over 3. Oops, sorry, wrong spot. Negative pi over 3. I often get the radius and the angle mixed up. Trying to get better. And negative 3. So negative 3 and negative pi over 3. So negative pi over 3 is right here. And negative 3 goes in the opposite direction of this, 3 units. That also describes this point. So this is actually unique to the polar coordinate system in comparison to the Cartesian coordinate system. If I jump back here, there's only one way to describe the point A over here in purple and blue. There's only one way to describe that using Cartesian coordinates. It's a unique pair of numbers describe this. However, in polar coordinates, there's an infinite amount of ways. So that will lead to some issues that we need to address later. But for now, let's pretend like it's a great thing. We can describe points in multiple ways rather than just a single way. With that said, though, I do want to move on. I want to now look at graphing the polar equations. So I'm going to start with the most basic of them, as you did in I'm sure, Algebra 1. Your teacher said, hey, graph this line, like y equals 4, x equals 2, whatever. I want to graph the line, so graph the line theta equals pi over 4. All right, so we're going to graph this thing. Let me go ahead and grab my polar coordinate system. I actually saved it from earlier. Move that right on over there. Before we graph it, though, I do want to just peek at, just like quickly remind ourselves why. Well, let's look at like the Cartesian coordinate system, x equals 4. We have a little grid here. What does this equation x equals 4 mean? Well, what it means is regardless of the coordinate that you plot, the x coordinate must be 4. So you can start just giving yourself a bunch of coordinates with an x value of 4. So 1, 3, negative 2. And then you plot these. So 4, 1, 4, negative 2, 4, 3. And as you do this, you start to create a locus of points. And that creates that vertical line. So x equals 4 vertical line. So with that said, let's go ahead and look at the line theta equals pi over 4. I'm going to do the exact same thing. I'm going to think about what possible coordinates have a theta of pi over 4. So just start like making up coordinates that have a theta of pi over 4. I'm going to go ahead and do 3 because I know 3 usually good. 2 is enough for a line, but 3 is going to make it a little bit more obvious. So I don't know, 2, 3. 2, 3, negative 1. Let's plot these. So pi over 4, that ray is right here, a little off. All right, so if I plot 2 comma pi over 4, that's going to be right there. 3 comma pi over 4, that's going to be right there. Negative 1 comma pi over 4, that's going to be in the opposite direction of this ray, so that's going to be down here. That's going to be right there. And then just keep plotting points. 0 comma pi over 4, 5 comma pi over 4, negative 5 comma pi over 4, and next thing you know, you have yourself a line. All right, so theta equals pi over 4, that is the equation for a line in polar. Similarly to how x equals 4 is a line in the Cartesian coordinate system. All right, is this the only way that we can describe this line? In Cartesian, x equals 4 is the only way to describe this line. But in polar, you could say, how about theta equals negative 3 pi over 4? All right, same line described differently. So polar has this kind of like special attribute that there's not a unique way to describe certain things. All right, so if that's a line, let's go ahead and look at another object. So cool. Let's look at the equation r equals 3. So what is that? Similarly to the previous page, we're just going to start collecting points that have the property that the radius is 3. So 3 comma whatever, 3 comma whatever, 3 comma whatever. 3 points is usually enough for me to start seeing what the object is. So let's go ahead, 3 comma, let's say pi over 2, 3 pi over 4. Let's do a negative 1, negative, what is that going to be? 4 pi over 3. Let's just do that. Cool. So let's start plotting these things. So 3 comma pi over 2. So pi over 2 is right here. And 3 out is 1, 2, 3 right there. We got 3 pi over 4. That's going to be over here. And so 3 out is right there. And then last but not least, 4 pi over 3, negative 4 pi over 3. So 1, 2, 3. Sorry, 1, 2, 3, 4. That's going to be kind of up here, comma 3. So I didn't mean for all my points to end up kind of clustered together, but that's what happened. You could imagine like pi over 4 comma 3, negative pi over 4 comma 3. That's down here. And as we start to collect these points, we see that, oh, you're going to see me try to sketch a circle. Uh-oh, I'm missing all over the place. We have a circle with polar coordinates, described using polar coordinates. And that is the first of many reasons why polar coordinates are nice. Describing curved figures like this is very easily done in polar. If you try to remember how you graphed circles in geometry, it was a complicated formula, x minus h squared plus y minus k squared equals r squared. That's nasty. But in polar, boom, just a single number. Kind of nice to describe this. Now, what would this be? This would be x squared plus y squared equals 9. And so not that bad, but this is certainly more simple. So polar coordinates going to have an advantage when it comes to circular things. Is this the only way to describe it using polar? The answer to that is usually going to be, for questions in polar, is this the only way? The answer is going to be no, usually. And that's because, I don't know, pick another thing that can describe this collection of points. How about r equals negative 3? That also works, because all the points with radii in the opposite direction are going to still be these points. So this is not the only way to describe a circle with radius 3 centered at the origin, centered at the pole. R equals negative 3 also does it. I believe that's the only other way, though. So there's 2 ways to describe a circle. And with that said, those are the only 2 equations I'm going to address in this video. In the next video, I'm going to start talking about much more cool-looking, complicated polar figures. Let's talk about converting. All right, so let's say I give you the polar coordinate 4 comma pi over 6. So pi over 6 is going to be roughly around here somewhere, and then 4, 1, 2, 3, 4 units out. So let's say I give you this point. Let's give it a name. Let's give it the name A. Knowing that this is the coordinate 4 comma pi over 6, let me go ahead and label that this is the polar coordinate. My question to you is, what is the Cartesian coordinate? I've already kind of addressed this, but let's talk about a formula that takes us from one to the other. So think about it for a second. And then once you've thought about it for a second, I'm going to go ahead and proceed. So pause if you need to. I'm going to go ahead and draw, like any good geometer would do, a right triangle, because that's its Cartesian coordinate. We need this length and this length. We need its x coordinate and its y coordinate, and we know certain things. We know the radius is 4, and we know that the angle in here is pi over 6. So I think that's all we need, right? Because we have trigonometry. How do I find out these 2 sides? Well, the x coordinate is going to be 4 cosine pi over 6, right? Cosine pi over 6 tells us the ratio in a unit circle triangle, but this one is 4 times as big, so we need to scale by 4. And then the y is going to be 4. sine, right? Sine is the y coordinate on the unit circle. This is not a unit circle. It's 4 times as big. And that is our coordinate. Let's just evaluate it real quick. So cosine pi over 6, that is, what is that, root 3 over 2? So times 4, that's going to be 2 root 3. And then down here, pi over, sine pi over 6, that's going to be 1/2 times 4, that's 2. All right, there it is, Cartesian coordinate. Converting from polar to Cartesian just amounts to right triangle trig. What is that just laid out for us? Given a coordinate. So we're going to go from polar to Cartesian. Right, given a coordinate r comma theta, the Cartesian coordinate is going to be r cosine theta comma r sine theta. And it's as simple as that, the conversion. So how to convert. Ooh. So converting from Cartesian to polar, that's a little bit more thought intensive. Let's go ahead and do it. So example. Let's say I give you the coordinate 5, 12. I call this point A, 5, 12. That means that its distance from the y-axis is 5. Its distance from the x-axis is 12. And we want a description of this with polar coordinates. So what do we need for polar coordinates? We need its radial length from the pole and its angle from the pole. So what is that here? So what is the radial length? Well, as most mathematics problems boil down to, we're going to use the right triangle. This is a right triangle. We have its legs, so we can find its hypotenuse. R is going to be the square root of 5 squared plus 12 squared. All right, I'll evaluate that in a second. The angle, well, what's the angle going to be? Well, I'll give you a second to think about it. But I need an equation that relates the angle to the two sides that I know. I also know the third side now, but let's just leave it with what we're given, the coordinates in Cartesian. All right. What's the relationship between an angle and a right triangle and its opposite and adjacent sides? That is the tangent. All right. So tangent theta is equal to 12 over 5, which tells us that the theta is arctan of 12/5. Now let's double check, because this is a first quadrant angle. Is arctan of 12/5 first quadrant? And yes, it is. Arctan of 12/5. Let me go ahead and tell you exactly what it is. It is hopefully less than pi over 2, a first quadrant angle. Arctan of 12/5 is 1.176. Cool. All right, that is a first quadrant angle. So we have arctan of 12/5. And if we want to be robust, we'll go ahead and write down this final answer. It is, let's see, 144 plus 25. That's 169, which is 13 square. So the square root of 169 is 13. And arctan, we just figured out, is 1.176. Cool. All right, so that is its polar coordinate. Right, we're going to go an angle of 1.176, a radial angle, and then we're going to go out 13. Cool. Oh, this was a Pythagorean triple the whole time. I bet some of you knew that right away. Now I want you to be careful, because here is a second example. Example number 2. Here is a coordinate. I want you to tell me what the polar coordinate is for -3, 5. So what is the polar coordinate here? All right. If you're tempted to just use the formula that we proved in the last page, you will be forsaken. Because if I do the square root of x squared plus y squared, right? The hypotenuse, comma, arctan of theta. You will be incorrect. This is theta right here. You will be incorrect. Now, your radial length will not be incorrect, but your angle with the polar axis will be incorrect. Let's just use this and then clarify that. So let's see. This is a -3. This is a 5. So that's going to be 9 plus 25, 34. Square root of 34. All right, so square root of 34 is my length away from the pole, comma, arctan of 5 over -3. Right? This is correct, but arctan of 5 over -3, what's that? Let me break out my calculator. Most of you hopefully are seeing that this is going to be in the wrong quadrant. So arctan of 5 divided by -3 is -1.030. All right, and that's because arctan outputs things in the first and fourth quadrant. That's what it's been designed to do. Arctan's range is from -pi/2 to pi/2. All right, you gotta be careful. Arctan's range is -pi/2 to pi/2. Our angle is in the second quadrant, greater than pi/2. How do we remedy this? There's two ways. So right now, this point here is describing the point exactly opposite of the one we care about. So how do we fix this? You can either make this negative, or you can add pi to this angle. If I add pi, I will get to the correct ray. Or if I make 34 negative, I will get to the correct point using the ray that I was given. So either of these is going to work. Square root of 34, comma, -1.030 plus pi, or -root34, comma, -1.030. So please be careful. The formula for going from Cartesian to polar is not as straightforward as polar to Cartesian. Right? Given an x and a y, right? We will be the square root of x squared plus y squared, comma, arctan of y over x if x is positive. Like, think about it. If x is positive, then we are a first or fourth quadrant angle, and arctan is going to give you the correct angle. But if xy goes to square root of x squared plus y squared, comma, arctan y over x plus pi, if we are in the second or third quadrant. So you got to be careful. You have to know the general location of x, comma, y if you're going to use a formula. But at the end of the day, you could just do the calculations and find out where your coordinate, which is the correct coordinate by inspection. So do be careful. There is no one formula for Cartesian to polar. You might need to add pi, and you might not. It just depends on which quadrant you're in. If you're in the positive x quadrants or the negative x quadrants. So just be careful. All right, so in this video, I'm just trying to hit all the basics. I got one last basic thing I want to talk about, and that's converting equations. So converting equations from polar to Cartesian or vice versa. Let's look at converting Cartesian to polar first. So Cartesian to polar. I want to convert x squared plus y squared equals 25 to a polar equation. Way number one, just look at it and know it's a circle and write r equals 5. That's cool. But the other way is knowing the conversions that we just proved. We just talked about how the square root of x squared plus y squared is equal to r in the previous page. All right, so if I square this, x squared plus y squared is equal to r squared. All right, so I can use that. I can do substitution. X squared plus y squared is r squared. Just go ahead and throw that in there. All right, and then I can methodically solve this. R is equal to 5, square root of both sides, or negative 5, plus or minus 5. I'm going to go ahead and choose 1, though, because I want this to be a function type of thing. All right, so you could just look at it, or we can use these formulas that we've been establishing. Here's another one. X equals 4. What is x in polar? X is r sine, cosine theta. All right, that is the conversion, all right, in general. So let's go ahead and substitute it in. X is equal to r cosine theta, so I'm going to replace x with r cosine theta, and then I'm done. I'm going to go ahead and divide by cosine theta, and I'm going to get 4 secant theta, all right? Because I haven't been saying this the whole time. I probably should have been. But the way we usually write functions in polar is a function of theta. So r as a function of theta. So, fun fact, r equals 4 secant theta. R equals 4 secant theta. That is a vertical line similar to x equals 4. So how do we describe a vertical line not going through the pole? Well, in this case, 4 secant theta. You can kind of imagine what any vertical line is going to be. R equals like a secant theta. So if it was like a negative 3, it would be over here. R equals negative 3 secant theta. We'll prove that later. Right now, though, let's look at the reverse direction. Let's look at if I give you a polar equation, right? Pi over 4, theta equals pi over 4. Maybe you remember what this is, maybe you don't, but theta equals pi over 4, that is this line right here, right? All the coordinates in the polar system, in the polar plane that have a angle with the polar axis of pi over 4. What is this in Cartesian coordinate systems? Well, one way to do it would just to be look at it, but as the problems get more complicated, we want to kind of think of a methodical way to do this. What is theta in the Cartesian coordinate system? Well, I know this, arctan of y over x is equal to theta. So I'm going to go ahead and substitute. So theta is equal to arctan of y over x. That's equal to pi over 4. And then how do I solve this? Well, there's several ways you can think about it. I'm just going to take the tan of both sides. And tan of arctan of y over x, that's just y over x. All right, arctan has a range that tangent can handle. And then tangent of pi over 4 is 1. And then final answer, multiply by x on both sides, and we get y equals x, a line that goes through the origin and has slope 1. So how do we convert from one to the other? We have these formulas that take us back and forth. Let's do one more. R equals 5 sine theta. All right, so R equals 5 sine theta. This one's not as obvious. I encourage you to pause and take a second. We can't use that, oh, I just know what it looks like already, strategy. So if you look at it and you think a little bit, do we have a formula for R? Do we have a formula for sine theta? We want to turn this polar equation into Cartesian. I think there's a few ways you could do this. You could rewrite r as the square root of x squared plus y squared. Right, that's one of our facts. Or you could mess with this sign. What I'm going to do, actually, I'm going to be clever about this. I'm going to multiply by r on both sides. R squared equals 5r sine theta. This looks a little bit familiar. R sine theta in Cartesian is the y coordinate. All right, and r squared is x squared plus y squared. All right, so we are now in Cartesian. Let's clean this thing up. Do you guys know what to do? All right, you've seen this before. I'm going to go ahead and complete the square, turn this into a circle. This is a circle if you think back to geometry. So I'm going to go ahead and subtract the 5y. And then I need to complete the square. So I'm going to take half of my b value here. That's 5 halves. Square it plus 25 over 4. And then now this is a complete square. Before I do that, though, I need to subtract 25 over 4 on this side. I got to do what I do to one side to the other. Oops, I totally meant to add that. All right, I added 25 over 4 to one side. I need to add 25 over 4 to the other side. And then I'm almost at the Cartesian answer. We have x squared, y squared minus 5y plus 25 over 4. That has been completed. We have y plus 5 halves quantity squared is equal to 25 over 4. I'm going to be clever and write that as 5 over 2 quantity squared. And there we have it. That is the equation of a circle in the Cartesian coordinate system. All right, we have a center at 0, negative 5 halves. And we have a radius equal to 5 halves. So boom. All right, fun fact, this r equals 5 sine theta is a circle with radius half of 5 and center at 0, negative 5 halves. Awesome. That doesn't feel right. Where did I make a mistake? Oh, this is negative down here. So this up here needs to be negative. So our center is actually a positive 5 halves. Sorry about that. Little mistake. All right, but we are to convert back and forth. We're using these formulas that allow us to convert coordinates back and forth. We can apply that to equations as well. All right, so that's the basics of polar. I don't think I have anything else to add. We looked at Cartesian versus polar coordinates, introduced a whole new system, and we used it a bunch of times. We graphed the coordinates, we graphed equations, and we we converted back and forth. We basically did all of Algebra 1, but with coordinates, polar coordinates, in like 20, 30 minutes. So that's kind of cool. Once again, this was lesson number 1, so there's a few examples in lesson 1 that I didn't do that you can do there. I just hit on the important things, and also page 796 to 803 in Larson if you want to get a second perspective. Happy Monday, happy Tuesday, happy whenever you're watching this day. Have a awesome day. Bye, guys.